Hello, am I audible? Good morning. Hello, am I audible?
Yes, sir.
Okay. So, uh, we were trying to do the solution of the current uh, in a thyristor converter, the exact solution, not the average solution. And let me just tell you again that thyristor converter is this. This is the converter. The major decision that we need to take all the time is whether it will be in CCM or DCM. For various kind of load situation. Load situation means the values of the structure of the load, more or less we have decided. Structure of the load, we have decided that it is R, L and a source. The source I wrote in the last class as VD. This is L, this current is ID, and this is R. So this is the converter, this is the supply VAC, and so major thing we need to decide is based on the given values of R, L and VD, whether it will be in continuous conduction or not. So in that respect, we know here VAC is given 325 volts, sine of 2 pi into 50t. Let us say this is the supply voltage. These thyristors are named as TH1, TH2 is here, TH3 and TH4. One thing we immediately can conclude that suppose firing angle alpha is equal to 30 degree. These are the things given, and the values of these things given. Let us say R is given something. So R is 1 ohm, L is equal to something 10 millihenry. These numbers will not matter at all, provided VD is greater than what? 2 Vm by pi cos alpha. Then, because if this thing is there, then irrespective of R and L values, this will be in discontinuous conduction mode. Discontinuous conduction mode. Why you can understand? You can understand why it will be so. Can anybody tell me why it will be so? Why I say if Vd value is greater than 2 Vm by cos pi cos alpha, then it is in discontinuous conduction mode. Why do I say so? What is 2 Vm by pi cos alpha in this case? 2 into 325 divided by shift pi into cos of 30 degree, right? So it is coming out to be if Vd is greater than 179 volts, 179.18 volts, then I can immediately conclude that it will be in discontinuous conduction mode. Why? Can anybody tell me why? Yes, somebody, please try. How is it in the continuous conduction mode? Suppose it is in continuous conduction mode, then what is it? What has to happen? The current in the inductor is continuous. So what has to happen? All the time in the continuous conduction mode, who are conducting? Either TH1 or TH4 or TH2 or TH3, right? Continuous conduction mode, if you look at it, you have at this angle, and it is continuous. So definitely what is happening is that the voltage that you are getting at the at the at the load end, or I will call it as V direct, what will be the voltage? You are fired at an angle alpha. This angle is alpha. You are fired at it. So this chunk of the voltage is coming at the output, assuming continuous conduction mode. That means the voltage is always, because thyristor is conducting, and this voltage is coming, and it will come, even negative voltage will come, right? Because the when TH1 and TH4 are conducting here, till TH3 and TH2 are fired, TH2 and TH3 are fired at this instant. That angle is 180 degree plus alpha. When TH2 and TH3 will be fired, until and unless that is fired, this chunk of the voltage comes, and then TH2 and TH3 fired, it will again jump back, and this will continue, right? So it can produce only this kind of wave shape, only this kind of wave shape. Only this kind of wave shape it can produce, right? And this kind of wave shape, in the continuous conduction mode, when it is producing, the average value of this, waveform, if we calculate the average value of the waveform, is, I know that 2 Vm by pi into cos alpha. For an angle alpha, it must mean, therefore, that it is equal to 179 volts for alpha is equal to 30 degree. When alpha is equal to 30 degree, then this is the voltage. So if that means in the continuous conduction mode, you can never get more voltage than that. You can never get, right? After that, if there is a resistance and there is a current, then I mean, you have to have some drop in the resistance and some drop in the inductive drop, let us say on average sense, is not there. So so alpha is equal to 30 degree. The maximum voltage of Vrect is this much in the average sense, 179.2 volts. So Vd has to be definitely less than that voltage, because at least less than that voltage. Because if it is precisely at that voltage, then Vrect is equal to Vd, and therefore Id is equal to 0. So that is one condition when no current is there, as if it is just barely conducting, barely continuous conduction. Okay, more and more continuous conduction if you want to put, then Vd has to be less and less. For example, if Vd is equal to 160 volts, suppose Vd is equal to 160 volts, then what is the average current Id? What is the average current Id then, if Vd is equal to 160 volt? Suppose Vd is equal to 160 volts. Then I can say that Id into R is equal to 179.18 minus 160 divided by Id is equal to divided by R. R is equal to 1 ohm. So it will be a current of 19.18 ampere. That is what it will happen. So you understand that for passing the current in the continuous conduction mode, the Vd has to be less than 179.18. So the moment you get Vd greater than that voltage, right, then you are you must be sure that you are in the discontinuous conduction mode, which is what the situation we have described here in the last class. That is, we said that Vd is equal to 190 volts. That is what we had said, that Vd is equal to 190. This also leads us to another interesting conclusion. Another interesting conclusion is, suppose the R is equal to 0. So then what can we say? R is equal to 0. Then what can we conclude from this circuit? Look at the circuit again. Suppose R is equal to 0. What does it mean? Just conclude in the similar way. What does it mean? R is equal to 0. Only inductor and a voltage source is there. This is voltage here. Okay. What can you say? Can anybody conclude something, say something, comment on it? Can you please comment on it? Huh? Can you comment on it? Just try, say something. What is your, by looking at the circuit, what can you say? What can you say? What has to be the situation? Continuous conduction or discontinuous conduction? What has to be the situation? Alpha is equal to 30 degree again. What has to be, whether the circuit will be, or it can be anything. How do I decide? How do I conclude whether the circuit is in CCM or in DCM? This is ID. You cannot tell. Then let me tell you that you think that if it is in CCM, then only one exact voltage has to be the value of VD. That is the only point it can be in CCM, because in the CCM its voltage has to be matching the VD, because average voltage of the inductor is 0. So VD must be exactly precisely matching the 2 Vm by pi cos alpha. So only at that point only we can say it is in CCM. What will happen? Let us say it is less than 2 Vm by pi cos alpha. What will happen? Suppose I have fired and VD I have chosen, VD, suppose VD is 160 volt in this situation, and I have fired the thyristor at 30 degree, and 2 Vm by pi, we have seen 2 Vm by pi cos alpha is equal to 179 volts, 179.2 volts approximately. So what will happen? What will happen? What is likely to happen? What is likely to happen? The DC voltage in the side is 160 volt, and you have turned on, you have fired the thyristor at 30 degree. What will you observe? The you do not, so if thyristor 1 and thyristor 4 conducts, and assuming that it is in continuous conduction, and it will be in continuous conduction. Why it will be in continuous conduction? Because never the current is getting an opportunity to come down to 0, right? Because every cycle the average voltage that is produced by the firing of this thing is 179.2, and the DC voltage is 160. So there is an effective positive voltage across this, right? Which means LdI by dt is positive, which means every cycle the current is increasing. Current will not come down to 0. ID will continue to increase. In this cycle, I am just drawing a straight line. It may not be a straight line, but it will increase, because the effective voltage across the inductor during this period is about 19.2 volts, right? And this positive voltage across the inductor will produce this half cycle, it will be increasing. This is, let us say, alpha to 180 degree plus alpha. Then subsequently another this thing 360 degree plus alpha, it will still increase. So thyristor 1 and thyristor 4 will be conducting, right? And here thyristor 1 and thyristor 4, and here thyristor 2 and thyristor 3. Thyristor 3 will be conducting, but the current will never come down to 0. So this is not the situation. This is not a stable situation, right? Here, suppose I apply a DC voltage to an inductor, the current continues to increase, then that is not a stable situation. That is not, it there is nothing to analyze. It will be infinity. If I wait for sufficient amount of time, the current will build up to infinite value. So that is not an interesting situation, or not a steady state operating condition of any circuit. So what we conclude is that this is more likely to, this circuit is valid only if it operates in the discontinuous conduction mode. In the continuous conduction mode, only one valid point is there, when Vd is precisely equal to 179.2 volts. Okay, that is meaningless operating point, because if these two things are balanced, then voltage across the inductor is 0. Circuit theory is, it is okay, but there is no current developed. There is now no meaning in that circuit, right? What will happen is in the less voltage case is that the current will continue to build, right? So continuous conduction mode of operation is ruled out. What is then possible is only discontinuous conduction mode of operation in this situation. So in the discontinuous conduction mode operation, what has to happen is Vd must be greater than 179.2 volts. But discontinuous conduction mode is a valid operating mode of the circuit. So don't think that since there is no resistance, there is no current, no steady state. Don't think that. It will be reaching a steady state, okay, in the discontinuous conduction mode, right? So let us see what is happening in the discontinuous conduction mode, right? Let us see qualitatively first, and then try to do the analysis of it. So what will be qualitatively happening? Here we observe that this is the AC voltage, and this is VAC, right? And your level of voltage is, let us say, here. This is what is Vd. This is what is Vd. Suppose you have fired at 30 degree. Let us say 30 degree point is here. 30 degree point is here. 30 degree you have fired TH1 and TH4. But note that, first note that, will it conduct? Will it conduct? What is this voltage at alpha? This AC voltage instantaneous value is Vm cos alpha, sin alpha, sorry, sin alpha, Vm sin alpha. That is the instantaneous value. That instantaneous value is less than sin alpha. So how much is that? Vm sin alpha is equal to 325 into sine of 30 degree. Sine of 30 degree is equal to 162.5, right? That is the right. Vm sin alpha is 325 into sine of 30. Okay, 325 into sine of 30. So 162.5, right? So this voltage is 162.5. Vd is equal to we have assumed that 190 volt, just some voltage which is higher than this voltage, 2 Vm by pi, in order to make the operation valid, and valid in the DCM mode. Only in the DCM mode it will happen. But here also you have to be careful in looking when it will start conducting. It will not start immediately conducting here, because Vd voltage, this side voltage, this voltage, Vd voltage, this voltage is greater than the voltage that is possible to get by firing TH1 and TH4 at alpha is equal to 30 degree. So it will not start to conduct, okay, because the thyristor is still reverse biased, even if you have fired, it is reverse biased. So what people have to do is, you have to continue to, that's why there are some pulses given, okay, high frequency pulse. It is not that just one pulse is there. Thyristor firing is, because then you will miss it, okay. You might have given a pulse, but at that point the input voltage was less than the Vd, right? So then TH1 and TH4 will fail to conduct. So that's why the people give pulses, many small high frequency pulses, thinking that at some point of time it will start to conduct, and that point is when these two things are equal. That is here, that is here. At that point these two voltages are equal, and from now onwards, from then onwards, okay, so from then onwards the converter, the thyristor TH1 and TH4 are forward biased. So what is this value? What is this angle? So again we calculate Vm sine of alpha dash, let us call this angle as alpha dash, is equal to how much? 190. So how much it will be alpha dash? Alpha dash is 162, not 162, 190 divided by 325. Okay, so that alpha dash is coming out to be 35.77 degree. 35.77 degree. At that precise instant, the conduction is possible because thyristor 1 and thyristor 4 are now forward biased. Okay, so it will continue to operate, conduct, right? It will continue for how long? How long it will continue conduct? Again, it will be reverse biased beyond this point. So, so what will? I'm sorry, it is not reverse biased. Okay, till that point, the input voltage is greater than the DC voltage. So what is meaning? Meaning is the effective voltage across the inductor L, this voltage, inductor L voltage across this inductor voltage, this voltage is now till that point it is positive. So what is the qualitative meaning of that? Qualitative meaning of that is that thyristor current will be positive. It is starting from 0 because in discontinuous conduction mode till it reaches this point, because this is positive area, the current in the current ID current ID is positive, right? Then I don't know when it will come down to 0, but I can make out what is this angle meaning. This angle must be meaning is 180 degree minus alpha dash. This must be how much angle? This must be 180 degree minus alpha dash. This is 180 degree minus alpha dash. That must be the angle at which it till then the inductor receives a positive voltage and the current builds up in the inductor, right? So current will build up from alpha dash to 180 degree minus alpha dash. Build up means it will increment. Why? Because the voltage is positive, the current has to increase. So shape is not important here at the moment. So current will increase. Okay. So what is this angle? This angle is 180 degree minus this. So that is 144.22 degrees. So the current will increase. Subsequently, what will happen? The thyristor 2 and 3 are not fired till another. It is fired at this point. It is fired at 30 degree. 30 degree means 210 degree. This is fired at 210 degree. That is 30 plus 180 degree, right? So that is the point when you have we are firing TH2 and TH3. So till that time, what happens? The current is maximum here. We can conclude that the current is maximum here, because beyond that the voltage across the inductor is negative. Why it is negative? Because VD is greater than instantaneous value of VAC. This is VD and this is VAC is less. So the current will fall. So at some point of time, I don't know in the beginning, I can qualitatively say that the current will fall somewhere. I should not show again increment. That is the wrong idea. I should show only decrement. So it will be somewhat like this, right? And this angle we are defining as beta. This angle from this we are defining as beta, or the extinguishing angle. That means when I'm sketching the current ID. This is ID. DC side current. AC side current is just plus minus, and DC side current is just a double frequency version of that. That means another current will be similarly produced here. Yeah. So this will be the ID shape, and you know how from ID how to find out what is IAC, right? Which is the AC version, flipped version of this current. Positive cycle, positive ID, negative cycle, negative ID. That's all. So the beta is called extinguishing angle, or in meaning it means that the current discontinuous conduction mode when the current again comes back to 0, right? So so you can see that power is going to the DC side because this ID current has an average value. Okay, if it has an average value, then there is no reason to think that power is not going. So there may not be any resistance. Resistance is not an essential component to transfer power. The power can go from the AC side to DC side with firing angle. With a value of DC voltage, which is pushing it into the discontinuous conduction mode. So DCM mode, the power transfer would happen, right? So now we'll try to find a precise solution of this current, right? So we'll write the basic equations and try to solve it. So let me do that. If there is any question, please tell me. Is there any question?
Sir?
Yeah.
So can you sketch the V-rect also?
V-rect?
Yes.
V-rect. Okay. Yeah, the V-rect is right. V-rect is let me do in color black. Let me do it in black. So V-rect will be what? You tell me. As long as the thyristor is conducting, okay, TH1 and T is this thing conducting, it will be just following the input voltage. So I'm just doing redrawing. I'm going this because the thyristor current is there. The ID is positive. ID is there. As long as the ID is correct, that this voltage is coming to the output. It will come a little negative as well. There is no issue. But here the current has dropped down to 0. Then what is your Kirchhoff's law telling you? What will be the V-rect voltage? Tell me. Look at the circuit and the current has become 0. So what will be the V-rect voltage? This is the V-rect voltage. Current in the inductor is 0. So what is V-rect?
VD.
VD. That's all. So after that, it will simply jump back to VD. It will jump back to VD, stay there for some time till subsequent firing angle happens. Okay, right? So then it will be again VD. So so that's what it will be happening. That means right. So it is here also the negative side. How do I draw? So negative side also I draw it like this. So up to this second side, this will be black. This will be 190 volt. It goes. It is not coming into conduction at 30 degree plus 180 degree. It will be coming into conduction at 180 degree plus 35 degree, 35.77 degree. That is this point. Till then, it will be 190 volt, and then when it becomes that, then it will go through the rectified version of the AC voltage. That means it will again go through this, go to this, go up to this, and then when it becomes again discontinuous conduction mode, it will again jump back to 190 volt and stay there. Like that it will continue. Like that it will continue. So moral of the story is that this point is 35.77 degree to the beta angle, not yet calculated. We will calculate to the beta angle. It will simply follow the input voltage in the positive cycle, and rectified input voltage. This is the rectified input voltage in the, this is VRECT, rectified input voltage in the negative cycle. Negative cycle implies TH2 TH3 conduction. Positive cycle implies TH1 TH4 conduction. So negative cycle, it will be the rectified input voltage, and otherwise the voltage on the discontinuous, when the current is not there for some duration, the current will not be there. that duration it will be clamping to the level of VD. This level is VD. It will be clamping to the VD level. Have I answered you?
Yes, sir.
Okay. Okay. So now let us see how this can be mathematically solved from the first kind of equations. So first kind of equation is that as long as ID is positive, if ID is greater than 0, this is the condition, and it is enough to take only half period, okay, because you know that it is periodic with respect to that, right? So what I will write it as that L di by dt, that is the voltage across the inductor, is equal to Vm sin omega t minus Vd, right? So I is equal to integration Vm by omega L minus cos of omega t minus Vd by Vd by L into t plus a constant k. This is a constant k or constant a or whatever you write it, constant of integration you write it. Okay, so what we know that it is 0 at an angle alpha dash. So we know that this quantity is Vm by omega L minus cos of alpha dash. Alpha dash, you understand why alpha dash, not alpha. You understand that I explained earlier, is equal to minus Vd. It would not have been alpha, and alpha dash would not have been different had I fired at 45 degrees, right? So this divided by omega L into alpha dash plus k. So this is the condition when at theta, general angle I am calling at theta is equal to alpha or omega t, let me call it omega t at omega t is equal to alpha dash id is equal to 0. This is id, ld by dt. Yes, ld by dt. So this is equal to 0. From that, this is the thing. So we'll get k from here because everything else is known. I have already calculated alpha dash. I know L is 10 millihenry. I know Vd is equal to 190 volt. L is equal to 10 millihenry, and Vm is equal to 325, and omega is equal to 2 pi into 50. So all the things are known. So I will calculate this. So after calculating this, this is by putting all that, I get it is 83.93 plus 37.7625 is equal to 121.6925. That is the coefficient of integration. So the full expression of current is ID is equal to minus Vm by omega L cos of omega t minus Vdc by omega L into omega t plus 121.6925. That is the current when current is greater than 0. Only that situation the current will be given by subsequently current is 0. That means it is valid between alpha dash to beta, valid between alpha dash to beta. this duration in not in time, in angle, this expression is valid, and we intend to know at what angle beta it will come back to 0. So to do that, we will have to put that id is equal to 0 again, and find out that that value, right? So what we'll do is we'll put 0 again is equal to minus, again we have to put Vm by omega L cos beta minus VdC by omega L. This is beta, omega t is equal to beta plus 121.6925. That is 0 at omega t is equal to beta. Id is again 0. Id is again 0. So from that we get this. So here by trial and error, you have to. This is what is a problem, that it's a cosine function, not easy to solve, and I don't know whether your calculator can solve this kind of equation. Hello, anybody can help me? Your modern calculator, your better calculators can solve this equation. Can you try? Anybody can give a comment whether it can be solved, or don't know?
So I don't think it can be solved in the calculator. Transcendental equations.
Okay. Transcendental equation, if it cannot be solved, you start little bit guessing it. And this guess is to be such that you don't guess that it will be 210 degree. It will be less than 210 degree, right? So it is, I have no better guidance than this, that it will be less than 210 degree. And you have to little bit do trial and error in this. So I had done this trial and error in this case, and I got a reasonable value. I didn't do too many iterations. I got a reasonable value, and I was happy with it. I got a value of around 205 degree. I got a value of beta is equal to 205 degree. Okay, I am saying that you don't worry too much about accuracy of this. A little bit error will be acceptable. There is no big deal when there is some small error, 5%, 10% error, provided you are formulating the equations correctly. Prior to this, everything you can do correctly. There is no issue. The formulation should be correctly done. And after that, if there is a little bit, don't make it huge mistake. But if it is more or less okay, then it can be accepted. So this is how we solve it. This is how one has solved it. But it has not given us the full feeling of the, we get a feeling of the current. The current waveform, you see there is a cosine function, this is a time function, and there is a constant, a very complicated current waveform. It has one cosine part and one this part and that part, and that is only curtailed between alpha dash and beta. Only in that portion it is, it has 3 combinations, and so that's it. So at between that portion, you will get that kind of expression, and you have to you don't have to go beyond that. You don't have to go beyond that. The waveform will look like this kind of thing. Waveform is this color waveform is looking like this kind of waveform. Okay. Now, what we need to do is, suppose somebody wants to know how much is the power really going to the DC side. So in order to do that, we need to do quite a few things, or somebody needs to know for the rating, how much is the peak current of this waveform, how much is the peak current. That also is not so easy to find out. Peak current, the waveform is there, but while it is maximizing is also not so easy to find out. This expression, when this ID expression, ID is maximum value, is not so easy to determine. So what we'll do is little bit do it in another way. That is our classical way or conceptual way. Conceptual way is, I need to know what is the peak value of the current. I know the peak value of the current is achieved when alpha, when it is reaching an angle of 180 degree minus alpha dash. This angle is alpha dash. This is alpha dash, and this angle is 180 degree minus alpha dash. So at that instant it must be reaching the peak value. So let us do the integration and find out what is the peak value here, right? So we can do the integration and try to find out that from that LdI by dt. So I have done that way. So what I have done is di is equal to whatever the voltage is coming across the inductor, that is alpha dash by omega to pi minus alpha dash by omega, and this is the inductor voltage. VL implies the drop across the inductor, which is nothing but di will be I max. You understand that, because initial current is 0. So di, if I integrate this di is equal to I max. I will write I will write it this way, IT max. IT max, that is the thing. Let me put capital ID max. So that is di, that is integration. So alpha 1 by omega pi minus alpha dash, not alpha 1, alpha dash by omega Vm sine omega t dt by L minus integration VDC. Let me write it directly. dc by L, and duration wise this omega I will bring here. So pi minus alpha dash minus alpha dash, right? So this is the amount the current has increased during this duration, alpha dash to pi minus alpha dash. So now it simply means that I have to put the values Vm by omega L cos of alpha dash minus cos of pi minus alpha dash minus VDC by omega L pi minus 2 alpha dash. So I have put the values 325 into 2 into cos of 35.775 divided by 2 into pi into 50 into 10 into 10 to the power minus 3 minus 190 VD, not VDC, VD. Let me be consistent. VD 190 by again 2 into pi into 50 into 10 into 10 to the power minus 3 into pi minus 2 into alpha dash. Alpha dash is 35 in radians, so 35.775 divided by 180 into pi. Right. So this is the thing, and if you do, I have done it. 167.863 minus 114.475 is equal to 53.388 ampere. So the peak value of the current we can find out. Okay, this may be required for the design of the inductor. You are putting an inductor, not only the value, you know the inductor. In order to know the inductor, it's not just enough to know the value of the inductance. You need to know what is the peak current passing through it and what is the RMS current passing through it. Why peak current is required is to probably know by this time that it is required for Li is equal to N phi. So it must not saturate. From the saturation point of view, we need to know the peak current of the thing. The more the peak current, the peak flux level is more. So therefore, we have to have more cross-sectional area of the inductor. So a design will never be complete. An inductor design will never be complete unless we know what is the peak current value of it, and with some more effort, you can also find out what is the RMS current value of it. but I'm not doing that. That is very cumbersome expression again. But I need to know how much power is transferred from the AC side to DC side, right? So I will do it assuming that it has efficiency is equal to 1. The thyristors have no drop. I just want to know how much, what is the current, average value of the current in the DC side, because this is DC side is one fellow is simple because this is constant 190 volt, and if I know what is the ID, that means the average current, even if it is discontinuous, I know DID, then I know how much power is coming to the load, and load is a battery kind of load. Load is a battery kind of load or a DC motor kind of load, which is VD represents the back EMF of the DC machine, so on and so forth. So I need to know what is the average current of the inductor. So that I will do by some integration of the basic expression. So let me take a so ID average must be equal to 2 by T because it is repetitive, 2 by T into alpha dash by omega to alpha, not alpha, here it will be beta, right? It will be beta by omega, okay, IT dt. IT means IDT dt. I'm trying to find out the average value of the current waveform. So that is equal to 2 by T integration. This expression, complete expression of this thing I will write, current expression found earlier, cos omega t minus Vd by omega L into omega t plus 121.6925 dt, and integration is from alpha dash omega by beta by omega, right? So if I do that, then this is equal to 2 by T minus Vm by omega square L sine of omega t minus Vdc by L into T square by 2 plus 121.6925 T, and this is varying from alpha dash by omega to beta by omega. Okay. So now we have to put all the values. Let me do that. Before that, 2 by T minus Vm by omega square L sine of beta plus Vm by omega square L sine of alpha dash minus Vdc by L into beta square by 2 omega square minus alpha dash square by 2 omega square plus 121.6925 into beta by omega minus 121.6925 into alpha dash by omega, right? So if we just put the values now, you will get that this will be equal to 28 point, the values you know, all the values you know, 28.11 ampere values you know. Beta already you have known, beta is already known, it's 205, you know, about beta is equal to 205 degrees. Beta, yeah, anybody?
Sir, like for finding the average current to the inductor, like can't you write the average current as the average value of the output voltage minus VDC by R? Like since the average voltage drop across the inductor will be 0.
Where is R? Where is R here? Where is R here? There is no R. This is the circuit. You just look at the circuit. This is the circuit. There is no R here.
Okay, sir.
So beta is equal to 205 into pi by 180 because you are not supposed to. This is all radian. So this is this. If when you are putting beta, you must be putting in radian. That is the thing. Alpha dash is already known. Omega is known. Vm is known. L is known. Everything is known. So it is 28.22 ampere to 1 ampere. So the power, output power is equal to now 190 into 28.11 ampere. So it is how much? 190 into 28.11. Right. So this is 503,041 watt approximately. Okay. So this is the way power transfer happens when in the discontinuous conduction mode, when there is no resistance. When there is no resistance. Resistance, until and unless it makes a significant difference, will not have too much of an effect. So we'll see the effect of resistance now. We'll see the effect of resistance now in the circuit. When we have a resistance, we should have the equation that we had already derived. Okay. So we had the equation. Let me write the equation one more time. We had derived this equation. This was the equation, right? Here you see everything is there. Beta minus alpha. In case of alpha is equal to alpha dash, you have to put that. So e to the power minus, this is the transcendental equation that we have to solve. So let me see, let me write it. I'll be able to remember it. Okay, let me write it first and then I'll copy it. This is when you have resistance and the resistance is only pushing it into discontinuous conduction mode because the VD is 190 volt. So it will always push it into this because it will demand more and more input voltage. So it will be more and more likely to go into discontinuous conduction mode because continuous conduction mode, how much input voltage it can give is limited. That is limited by 2 Vm by pi cos alpha. It cannot go beyond that. So resistance will only push it into discontinuous conduction mode. Okay, so that is qualitative understanding first. First is very much required to understand this thyristor converter. In fact, is more difficult than understanding the conventional DC to DC converters that we have learned because they are very clear on and off durations are there. Here the current decides when it turns off, the thyristor turns off. So it is rather difficult. And so concluding it is the first conclusion is whether it is in CCM or DCM. And in that you should observe the things. You should observe the value of the DC voltage. And as I said in the last class, that if this VD is greater than 2 Vm by pi cos alpha, it is bound to be in the discontinuous conduction mode. But if VD is less than that, 2 Vm by pi cos alpha, it may or may not be in discontinuous conduction mode, depending upon the values of R and L, the time constant of the circuit. Right. So let me write this equation one more time. So the equation is e to the power in DCM mode, DCM, e to the power minus r by omega L into the general thing is theta minus theta. Okay, let me write it, theta minus alpha dash in this case. Let me write alpha, and so that you have a general equation, because alpha may be equal to alpha dash, right? Theta minus alpha is equal to VDC by VM, VDC not VDC, VD by VM minus minus R by Z. Z is equal to square root of R square plus omega square L square. That is Z. Sine of this is theta minus phi. Phi is tan inverse omega L by R. That is phi. We call it phi. Theta minus phi. Okay, that is theta minus phi divided by, it is a ratio. Sorry, so the equal to sign may be better put here. So it is again structurally almost identical, Vd by Vm minus R by square root of R square plus omega square L square sine of the known one, theta, alpha minus phi. That is alpha minus phi, and phi I have already defined. What is phi? Right, this would be the transcendental equation, solution of which will give us beta. Here we have to find out when, at what theta is equal to beta, this equality holds. That has to, you have to find out the theta is, and that angle is called beta, right? Extinguishing angle. Theta is a general thing, and at theta is equal to beta, this equality will hold, right? So in this case, let us say that we have taken earlier R is equal to 1 ohm, we had taken L is equal to same 10 into 10 to the power minus 3, omega is equal to 2 pi into 50. Okay, so let us find what is phi. Phi is equal to tan inverse omega L by R. So I have calculated that tan inverse omega L by R. Calculated that, yes, tan inverse omega L by R, and I have calculated that to be 72.343 degrees. Okay, so let us then try to find out, and that is cos phi. This R by square root of R square plus omega square L square is nothing but cos phi. In this case, it is about 0.3033. So overall, the expression is that e to the power minus, you see that R by omega L, R by omega theta minus alpha. So that is 0.3183 into beta minus 35.775 degree, because that is what it is, into pi by 180 degree, just to have it in radian, is equal to this expression is 190 by let me write it here, Vd by Vm is equal to 190 divided by 325, which is equal to 0.5846. So let me write it here. Let me write 0.5846 minus 0.3033 into sine of theta, not theta, it is beta. At beta, it is, they are becoming equal. Beta minus 72.343 degree divided by 0.5846 minus 0.3033 sine of 35.775 minus 5 is equal to 72.34 degrees, right? So again you have to solve by trial and error, and I have done it, and I get nearly equal to, I am not very sure very correctly, it is 192 degree approximately I am getting it, right? So I solve it and get 192 degrees. So you can see qualitatively what has happened because of the resistance, presence of the resistance, it is conducting for less time, which is what is supposed to happen, because some part of the drop is consumed in the resistance, right? The input voltage, the current, when the current is flowing, I into R is happening, so some drop is counteracting the inductor positive voltage, because IR is actually opposing the inductor voltage. So therefore it is coming down to 0, the current is falling to 0 much earlier, somewhat earlier, not much earlier but somewhat earlier. If there is a resistance here, suppose there is a resistance here, when there is a resistance, the resistance drop is working against the inductor polarity drop. This is, see the polarity convention, plus is coming here, this drop is opposing the inductor, right, inductor voltage. So therefore this effective voltage across the inductor is reducing, and as a consequence this will be coming down to 0, not at 205 degree but at 192 degree. So the current waveform now will look like, if I sketch it, this is the voltage, this is your alpha, you have fired it here, is here, but actual conduction has happened, let us say in here, actual conduction has happened here, okay, and it has gone up to 192. So this is 180, somewhat here, somewhat little extra than that, okay. So the current is now going right. So this is the point, this is the beta, this angle is beta, this angle is alpha, and this angle is alpha dash, this angle is alpha dash. So and this is ID, right? So this is what will happen, and the beta is 192 degree. It will be less, it is less than 205 degree that we found when R was 0, right? Similarly, from your common sense now, you can put R is equal to 10 ohm, right? You put R is equal to 10 ohm, keeping other values same. Suppose you put R is equal to 10 ohm, other values remaining same, 10 into 10 to the power minus 3 Henry, and Vd is equal to 190 volt, and other values all are same. So then you would see, so only change is in the resistance. You expect this beta to be even less, and I checked it myself. I checked that it is coming out to be beta is equal to 159 degrees, okay, with 10 this thing, okay, right. All right. I had also, for better understanding, I did a little few more things in this thing. I put alpha is equal to 45 degree, so that alpha dash issue was not there, and for that R is equal to 0. Other things are same. So then I got beta Vd is equal to still 190. So I got beta is equal to 204, almost same value, almost same value. So I got beta is equal to this. When I had used that I'll come a little later. So as far as this is concerned, it is for this is for discontinuous conduction mode. So what happens in continuous conduction mode? What happens in continuous conduction mode is that first you have to observe that this Vd is substantially low, right? Vd is equal to 135 volt. I have taken Vd substantially low. You may choose Vd more than that, but then you should use inductor. If you have the same 10 millihenry and if you choose Vd is equal to, let us say, 160 volt and L is equal to 10 millihenry, okay, as it was earlier, you will still get DCM. I have seen that only with Vd is equal to 135 volt and L is equal to, not only with, maybe some nearby value also will work, but L if I do not change, if I keep 10 millihenry, I need to reduce Vd substantially from 190 volt and R is equal to 1 ohm. I will get a continuous conduction mode in this situation. This will be CCM. So that is the point I was mentioning, that even if Vd is less than 2 Vm by pi, you are not assured 2 Vm by pi cos alpha. You are not assured that it is not assured that you will get this here alpha is equal to 45 degree. It is not assured that you will be getting continuous conduction mode of operation. Okay, 2 Vm by pi cos alpha is here 146.30 volts. So 160 volt definitely will get DCM. There is no doubt about it. What I'm saying is 146.30 volts. If you had made it slightly less, maybe 142.30 volts, you would not have got a continuous conduction mode situation. Continuous conduction mode situation requires a reasonable amount of difference between this and this, and also depends upon the value of R and L. So L by R time constant, depending upon that, you will be able to go to continuous conduction or discontinuous conduction mode of operation, right? So let us see how a continuous conduction mode of operation can be analytically solved. So what is the situation here? Qualitatively, first you see what is the situation, that current what does continuous conduction mode mean? Means it is the voltage. Okay, you have fired at an angle alpha. Okay, current is not zero here. Current is something I do not know. I cannot immediately know. So here the unknown variable is coming here. Current is here somewhere. Okay, but only thing I know that because it is continuous conduction mode, when the angle is pi plus alpha, when it has come to pi plus alpha, this current has come back to the same precise value. That means it has gone up and down. Okay, not sinusoidally in any other complicated manner. It has gone up and down, but it will come back to the, let me then remove that, otherwise I may give a wrong impression that it is such a nice waveform. Let me say that it is let me do it in red. Let me do it in red. So it has gone up and down, right? So only thing that is assured is this level of current is ID naught. So is this level of current ID naught, initial level of current, and then again it is periodic. Then again it is periodic. It is periodic. That is the current waveform ID. It is in a form an imperfect current source. You remember sometimes for simplicity to indicate that it is in CCM mode, whenever I put a current source in the DC side, you will be understanding that I mean that the converter is in continuous conduction mode. whenever I put a current source load as a current source. So that means I am putting it as a I am ensuring that this thing is continuous conduction mode. But continuous conduction doesn't always mean that we have to put a current source. Here the structure is that we have a R, L and a voltage source also. Okay, that could put it into CCM. CCM operation is not assured, but could happen, right? Could happen when the first general condition is that Vd must be less than 2 Vm by pi. After that, it will also depend upon L by R time constant. The L by R time constant, the higher, the more likely it is in continuous conduction. L higher, L by R higher means L is higher and it will be in continuous conduction mode. And in the continuous conduction mode, what you know is what time the thyristor conducts. Actually, thyristor is conducting all the time. Thyristor conducts means thyristor 1 and thyristor 4 is starting to conduct here. This is TH1 and TH4 zone. TH1,
Sir?
TH4. Yes.
So like as you said that if 2 Vm by pi cos alpha is greater than VDC, then the converter can be in CCM or DCM. So like how do we exactly determine that thing in that case when 2 Vm by pi cos alpha is greater than VDC?
That is the first expression, no? You didn't attend the class. Like if a thyristor converter is there and you fire at an angle, the average voltage that you produce is how much? Suppose you are firing and assuming continuous conduction mode, the average voltage is a chunk of the AC voltage, right? This is alpha, this is 180 degree minus alpha. This is alpha, this is 180 degree minus alpha. So this is the voltage that is going to the DC side. And this value, if you take the average value, that expression becomes 2 Vm by pi into cos alpha. That is the average value of the voltage. That is possible. So continuous conduction mode implies that V rectifier average has to be 2 Vm by pi cos alpha. So if this voltage 2 Vm by pi cos alpha is greater than Vd, right? It is greater than V. Then the balance is going to higher. Balance is going to the resistance. Balance is going to the drop is going to the higher. It is going to the resistance. So that resistance and this voltage difference is producing the current. However, if the inductor is too small, even under that condition, there will be some average positive current, but the current may come down to 0 if the inductor is too small. This inductor is too small. But if that is why the time constant is coming, the effect of time constant is coming. If the inductor is large, then inductor, whether it is in CCM or DCM, the average voltage drop across it is 0. So the average current wise it is not hampering. It will be the same whether it is in CCM or DCM, right? However, what will be happening is that in the inductor average current is same. But what will be happening is that if it is in DCM, the current will come down to 0 because there is no inductor which is holding the current. But if the inductor value is sufficient, then you will see that the current is shape changing and it is becoming like this, where it is above 0, it is going and changing because inductor is making it continuously flattening up. The more inductor you give, the more it will be. Though inductor is on an average not dictating the equation. Inductor in the continuous conduction mode is not dictating the average equation. Same average current will be going in the continuous conduction mode. But what will happen is the inductor current shape will be different. And at some point of time, if the inductor value is too small or L by R time constant is too small, then you will see that discontinuous conduction mode will start. Discontinuous conduction mode will build in. So moral of this story is in short that for continuous conduction mode, 2 Vm by pi cos alpha has to be greater than Vd. That is a necessary condition. Sufficient condition, it is not a sufficient condition. For sufficient condition, you have to also look into the L by R time constant. And only when it is not only the input, the 2 Vm by pi cos alpha is not only greater than this, but the L by R time constant is sufficient, then we can say that it will be in continuous conduction mode. And when it is in continuous conduction mode, then initial current ID naught must be equal to the pi plus alpha duration current ID naught. That is the condition of steady state. Steady state is considered to be a periodic situation. So initial current must be equal to the final current. So that is the way we have to think. And 2 Vm by pi cos alpha sanctity is coming from the point of view that if it is in continuous conduction mode, this is the voltage it can produce. In continuous conduction mode, it cannot produce anything greater than that. The rectified voltage average, it cannot produce, it is helpless. So only adjustment is possible in the load side. In the load side, if it has sufficient time constant like L by R, and if the voltage is low, this is sufficiently low, at least somewhat low, then lower than 2 Vm by pi, then only the equation can be balanced. Otherwise, you see the equation cannot be balanced. The V rectifier must be equal to this drop plus this drop, right? It must be that, right? So this drop plus this drop is only it is balancing in that manner in the continuous conduction mode, okay? And the inductor then requires it to hold, the current to hold, right? The current, because otherwise the current falls, the continuous conduction mode goes, and 2 Vm by pi cos alpha equation goes. 2 Vm by pi cos alpha equation is happening only if it is a continuous conduction mode, right? So continuous conduction mode, in order for it to happen, the current has to be continuous. And when it is continuous, this voltage is 2 Vm by pi cos alpha. And when it is 2 Vm by cos alpha, that is balanced by this drop plus this drop, right? Right? And inductor value is such that it is maintaining the current above 0 all the time, right? So this is why we require a voltage V rectified 2 Vm by cos alpha greater than this, because otherwise this drop how will accommodate? You have to accommodate the resistive drop. So that's why it has to be greater than 2 Vm by cos alpha has to be greater than Vd, right? As well as this second condition is that the inductor is sufficient, large enough to keep the current level above 0. This is above 0. You see, the inductor is such that it is not allowing too much ripple in it. It is not allowing. So suppose inductor reduces, then the current ripple comes down. Then further reduces, it comes to 0. And further reduces, it is in discontinuous conduction. And then the assumption goes that that the voltage, rectified voltage, is 2 Vm by pi cos alpha, because now the voltage is more. Because the DC level of the voltage, you have seen the waveform I had drawn. I had drawn a flat portion plus AC portion. So the flat portion is giving more voltage. So in the discontinuous conduction mode, the output voltage is more than what it could have been in the continuous conduction mode. Okay, so let's solve this equation. The solution is exactly the same way. You will write the expression and with ID naught in it. Instead of 0, you will write ID naught. So let me write that and then solve for ID naught. That is what we have to do. So you will write it as so CCM equation. What you will write it as initial current is ID naught. That is the current. That must be equal to Vm by Z sine of alpha. It must be alpha. Alpha dash is not possible. It is always continuous. So thyristor has turned on. The moment you are fired, the thyristor is on. Minus tan inverse omega L by R minus VDC by R plus A e to the power minus R into alpha by omega L, right? This is what we had. That means we are saying that at omega t is equal to alpha, ID is equal to ID naught. From the basic equation that we had derived earlier, this is the expression. Because you see, this is the idea is that this is a kind of particular integral, and one is the complementary function. There are two sources. The first source is a sinusoidal source, so it is producing a response which is Vm by Z sine of alpha minus tan inverse alpha will be omega t in the general case, alpha minus tan inverse omega L by R, right? minus Vd by R, because there is one DC source here, Vd, let me put it Vd by R, plus A is the constant of integration that we require to match the initial condition, and this is what the time constant e to the exponential term, but we are calculating omega t is equal to alpha, so that's why this value is specific value of omega t is equal to alpha has been put in the equation. So this is the situation, and the same equation is at omega t is equal to pi plus alpha. Also will get id is equal to id naught, because we are doing steady state solution. The circuit is now repetitive or periodic, so that must be also that second equation, that therefore is equal to Vm by z sine of pi plus alpha minus tan inverse omega L by R minus Vd by R plus A e to the power minus alpha by omega L, right? Pi plus alpha by omega L, right? Right. So what we get, I have to solve to know this thing. I have to first solve what is A. So what is A? Constant. So A is equal to, you subtract it, both side id naught cancels, this will cancel, id naught, this is also id naught. So I subtract equation 1 and 2, then this thing cancels. So you then get A is equal to Vm by Z into sine of pi plus alpha minus tan inverse pi plus alpha minus tan inverse omega L by R, okay, minus sine of alpha minus tan inverse omega L by R, right, by divided by e to the power minus R L alpha by omega L minus e to the power minus R pi plus alpha by omega L. That is the unknown constant of integration A. And once we know A, we know the equation. Only unknown thing is here A. So if we know, it will be. But by equating these two things, we can find out what is A. So I have done it for the example I was giving. I was giving an example of VDC is equal to 135 volt, R is equal to 1 ohm, and R is equal to 1 ohm. What else is required? VM already I have said 325. L I have said is equal to 10 into 10 to the power minus 3 Henry, 325 volt, and omega is equal to 2 pi. Omega is equal to 2 pi into 50. So with these things, if you calculate, we'll get this is equal to no, I didn't do the calculation. I didn't do, I missed the calculation. Okay, so you may calculate it and let me know what it will be the value. What will be the value? In fact, uh, in fact, if you put these values, still it is in DCM. Still it is in DCM. Even if it is 1 by 135 volt, 2 Vm by pi, 2 Vm by pi cos alpha is equal to 146.30 volt. I am getting, still I am getting DCM because I am getting alpha beta is equal to 212 degrees. Here alpha was 45 degree, alpha was 45 degrees, sorry. So I didn't do the calculation. I have to put higher value of L. So what I am saying is, to do L, to understand, you first put L is equal to this, you will see that it is still in DCM. But if you put L is equal to, I had it is LT is equal to about 50 millihenry, same values, 50 millihenry, VDC is equal to 135 volt, R is equal to 1 ohm, Vm is equal to 325 volts, and omega is equal to 2 pi into 50. You will get, you will go into CCM, and you have to then find out what is ID naught, small ID naught. Please calculate. I forgot to calculate that. I didn't keep the number here. You may calculate. First calculate, put L. So this, for this you have to put L is equal to 50 millihenry, not L is equal to 10 millihenry, because 10 millihenry it is be still in DCM. Even though VD is less than, even though VD is less than 2 Vm by pi cos alpha, right? Even though Vm is less than 2 VD is less than 2 Vm by pi cos alpha, it will be still in DCM. But this condition it will be in CCM, and ID value I didn't calculate. I have to find out later. So the method is simple. Here also you have to find out A, and once you know A, then you know the current expression. You know the current expression. You can put A value here, and we will get the value of ID naught, initial value of the current. Right. One more thing I will tell, but yeah, tell me a question, some question if you have, please.
Yes, sir. In this case, we find the value of A and we find the expression of I, and we see that if it is becoming 0 before pi plus alpha, and if it is becoming 0 before pi plus alpha, then it is in DCM, right? Hello?
Yeah. What is that thing you are asking? I will say that
I mean, how do we find if it is in DCM or not, like from the current expression?
No, say it again. I didn't get the question. Say it again.
Yes, sir. Like by substituting L is equal to 10 millihenry, we get a value of A. So
We get a value.
and then we get the current expression, and then how do we find if it is in DCM or not?
I believe you can check that. I believe then you will get a ID not less than 0. Okay.
At pi plus alpha, we'll get ID less than 0.
What I'm saying is that you put 10 millihenry and find out A. Okay.
Okay.
Hello. Okay. First thing is that you use this equation and find out A, putting 10 millihenry. Let us say. Okay. You have found out. You have initially assumed CCM, use CCM equation and found out A. Okay.
Yes.
And this A then expression you then put it in ID naught. Okay. A value put it here.
Yes, sir.
Right, and put alpha is equal to 45 degrees. Okay, you will probably get in, I will also cross check and tell you next class, you will probably get ID not less than 0, which means that your assumption is not correct. Okay.
Okay.
So ID
usually
actually comes to be minus 37 ampere, I think. For the first.
Great. That means that my assumption that it is in CCM is not correct.
Okay.
That is not correct. I had assumed that in CCM, and assuming CCM I had found out A, and then with using that A, the current expression I got, and then I had used alpha value is equal to 45 degree to find out what is the value of the current at alpha is equal to 45 degree. When I see that the ID naught has become negative, I know that it is not possible to be negative because the thyristor converter direction is such that ID naught cannot be negative. It can be 0 or greater than 0. So therefore, my first assumption that it is in CCM is not true. Then I have to go to the DCM mode of operation and use the DCM equations just prior to that. Okay. But however, if you put L is equal to 50 millihenry, you will get such a value of A that it will put the current into continuous conduction mode. Okay, that is the point I'm trying to raise. When I'm trying to tell, and then only you will get ID naught which is greater than 0. Greater than 0 value will be coming out. Find A now, and then ID naught will get it as greater than 0. Right. I had done, I forgot to do this one, but I had done much simpler one in the structure wise. Like, what is the simplest structure in this case? Continuous conduction mode, that VD is equal to 0. That is more likely to make it continuous conduction mode. So I had done that, and I will tell you what I got. So what I considered is that the more likely case of continuous conduction mode is possible, though I am not so sure that all the time it will happen, is possible if I take a structure of RL load, just R and L load. Okay, so I take the structure of RL load, and firing angle is alpha is equal to 90 degree, 30 degree. I had taken R is equal to 1 ohm, and L is still 10 millihenry. Till then, this is 325 volt. So, so if we saw that I calculated this A using this. So A was this one, Dm by mod Z into sine of pi plus alpha minus tan inverse omega L by R minus sine of alpha minus tan inverse omega L by R, this divided by e to the power minus R alpha by omega L minus e to the power minus R pi plus alpha by omega L. I have put the values 325 by 3.3 approximately. This is mod Z. Mod Z is nothing but square root of R square plus omega square L square. It is approximately 3.3 ohm. So 3.3, and sine of pi plus 30 minus 70 tan inverse omega L by R. Tan inverse omega L by R is 72.343 degrees. So it is 72.343 degrees minus sine of 30 minus 70.343 degrees divided by e to the power minus 30 into pi by 180 divided by 2 into pi into 50 into 10 into 10 to the power minus 3 minus e to the power 1 by 2 pi into 50 into 10 into 10 to the power minus 3 into 210. You understand why that is 210? Because alpha pi plus alpha is 210. Pi by 180, right? So this will give me a number which is 248.087. A is coming out to be 248.07. So the ID expression is coming out to be 98.48 sine of omega t minus 72.343 degrees plus 248.07 e to the power minus t by let me write it compact way, e to the power minus 0.318 t. That is the expression of the current, right? VDC by R, that part is not there, so that is the expression of the current. So V, that is ID, and the average value of the current, not average, ID naught. What is the, this is the current expression. So ID naught is putting alpha is equal to 30 degree, omega t is equal to 30 degree. So I'm getting a number of 93.48. Sorry. Minus 93.84 plus 248.07. Did I make a mistake here? It is, I am getting 154.229. Did I put it wrongly? Oh, this into t is equal to that one. So calculate it. One minus t is equal to 30 into little correction is required into yeah, I'm getting 116.146 ampere. Please check also. So this way you can calculate. So this means that it is in continuous conduction mode. That is what it is implying. Interestingly, you may check that if R is equal to 10 ohm, what happens? You will see that if R is equal to, instead of 1 ohm, 10 ohm, okay, it will go into DCM. It will go into DCM. So you see the impact of the things. L high value, it is good. R high value, good means it will be in CCM, and R high value, it will go towards the DCM. So that is well known. From the concept itself, we can understand. So L increases, it moves towards CCM. R increases, it moves towards DCM. Right? All other quantities remaining same. If R is equal to 10 ohm, you will go into DCM condition. Any question? Okay, so this is another way the load can be structured in thyristor converter. That is what the inductor is not on the DC side, but it is in the AC side. That is possible. Whether that inductor is a leakage inductance or whatever it is, this is R and this is VD, R, VD, but in the source side the inductor has come. Inductor has come in the AC side or the source side. Suppose it is like that. Then what qualitative differences we can think, or quantitative differences we can think, and how to analyze it? TH1, TH4, TH2, TH3. Anybody? Any insight? CCM, DCM, think to both things, CCM, DCM. Whenever this sort of questions are asked, you should think whether in CCM or DCM. So what will you think here? CCM or DCM? Let us think DCM first. Suppose it is in DCM. What difference will it make? Compare it with this. Compare it with this, the earlier case. Compare with this. Think and you decide what way CCM and DCM, what way DCM in both are comparable. Assuming that same value of R, L and VD have been used. What way? Are they different or are they same? What way they are different, what way they are same, and what do you conclude? Both are in DCM. In fact, if I ask you this question, R is decided, VD is decided. Keeping them same, if I put the inductor from here to here, what difference will it make? In the input current, in the voltage, Vrect voltage. Here now I will call this as Vrect voltage. I was calling this as Vrect. What way these two things will make a difference? Just think that the same value of inductor from this side I have put in the input side. AC supply system is same, frequency is same, firing angle is same. So will it be different or not? What way it will be different? I think it will be different. The moment TH1 and TH4 is on, okay, TH1 and TH4 on, the circuit is identical, no? This supply source, L, R, VD. Only thing is that V rectifier at this moment you are tapping from just R and VD. Let me put the L there, so then comparison will be easy. Let me put the L top and L in the top, R in the bottom. So at present, whatever the V rectifier you are looking at V rectifier as this part. Circuit is identical because it is in discontinuous conduction mode. When in the discontinuous conduction mode, why I am giving so much importance to discontinuous conduction mode? Because in the discontinuous conduction mode, current comes down to 0. So there is no interference between firing pulses of TH1, TH4 and TH2, TH3. Look at it this way, that if this is the voltage, you have fired at this point and you are firing at this point. This firing is for TH1, TH4 and this firing is for TH2, TH3. But the current has come down to 0 somewhere early. It is not going into the zone of TH2 and TH3. Current has started from 0 and come down to 0. So they are pretty much independent of each other. Okay, the circuit is just the same. This equivalent circuit in this portion is the same as this portion. It is series RLC circuit. So in DCM mode, there is nothing different. The inductor is on the AC side or it is in the DC side. There is no difference in the DCM mode, right? Got it? Then what way this can be different? If the moment thyristors are conducting, this circuit and this circuit are identical. Okay, you may say even CCM mode when they are conducting they are identical. But in the CCM mode, yes, when they are conducting they are identical. That's true. But there is a complicated zone in the CCM mode which is not there in this structure. Okay, which is not there in this structure. In this structure, what happens? If this is a CCM, suppose the current is this. A CCM, what happens? It just commutes, right? It just commutes in this side. Instead of TH1, TH4, it will commute and current will go to TH2 and TH3. This current will go from here to here. No, nothing. And input side has nothing dictating. It is not dictating. There is nothing dictating. It is just reflecting the current waveform, ID. Whatever the current waveform, it is getting reflected here. Positive cycle, positive value, negative cycle, inverted value, flipped value, right? So commutation is not doing anything abnormal here, because the moment if you turn on TH2, immediately TH1 turns off. So circuit is stable. Circuit is just taking another path. The current is simply taking another path. Okay. However, if there is an inductor at the input side, you see that is not happening. That will not happen. The current is continuous. You see that current is continuous. I'm talking about the CCM mode. So current is continuous, and in the beginning, let us say TH1 and TH4 were conducting. Right? It was conducting like this. TH1, TH4 is conducting. Right? And at an angle, what we do? At an angle alpha plus 180 degree, we fire TH2 and TH3, hoping that TH1 and TH4 will turn off. But will the TH1 and TH4 will turn off? Why it will turn off? What causes it to turn off? In this case, the moment TH2 is fired, you see that the voltage is negative. The moment this point is here, you have fired, the voltage is immediately negative. This voltage is negative because you have fired at this zone. When the input voltage is negative, it is negative, and the current can afford to go there. However, in this case, what is happening? You have turned on this fellow. That means you have almost like shorted these two fellows. You have shorted this and this, right? This will turn on because this was forward biased and you have turned on. So this will turn on. TH2 will turn on. So there will be a zone when both TH1 and TH2 are on. And then slowly current will change from this side to this side, this thyristor to this thyristor. It will not happen immediately. There is a duration between which this input supply system is shorted through the inductor, shorted through the inductor. And you know that TH1 and TH4 are conducting same time, and TH2 and TH2 will be fired at the same time. So similarly, TH3 and TH4 are shorted at the instant when you are firing here at that instant for a very small time. It is not a very long time, but there is a difference. Is that this bridge is now shorted. All four thyristors are conducting for some time. Okay, and the current as if this voltage is 0. This voltage at this point is 0. Okay, this voltage at the thyristor end is 0. You are giving a 0 voltage here. You may even think that the current is trying to flow from this side to this side. You may also think that way. Okay, but will not really consider that. Will not at the moment consider that. We will just consider these 4 things are on. Okay, so these 4 things are, when they are on, these 4 things are on, then the current from here, which was earlier conducting, will reduce and the current to TH2 will increase. TH1 current will reduce and TH2 current will increase. Similarly, TH4 current will reduce, TH3 current will increase. And in that, these 2 things sum together will constitute this current, right? So to better make it a circuit which is meaningful, we also have, in the continuous conduction mode, we also have an inductor in the DC side, because that is what we require for making this current continuous, because otherwise we are seeing that the load is trying to send power in the reverse direction, which we don't want in this application. In this application, power we want to send from AC to DC. We don't want an unnecessary interference. So we have put an inductor here in the DC side to ensure that the current is continuous, and this is called a commutating inductance, meaning that it is a lines leakage inductance. It is not what we want, but it is a non-ideality present in the circuit. This is actually the filter inductor to make the current continuous. Okay, even if in this case you consider a filter inductor and a leakage inductor, if these 2 things together make the current discontinuous, then it is discontinuous. No issue. No, there will be any difference whether the small leakage inductance is in the AC side or DC side. Okay, provided these 2 things, inductors are coming in series. Now they are coming in series, and after coming in series, the effective inductor is L plus LC. If L and LC mix it in DCM, then it doesn't matter whether L plus LC is in the AC side, L plus LC is in the DC side, or LC is in the AC side and L is in the DC side. It doesn't make a difference in the discontinuous conduction mode, right? However, it will make a difference if L value is such that, R value is such that, if the circuit is in continuous conduction mode, that means this current at the load end will have to be continuous, will have to be maintained, but there is an undesirable leakage inductance which will always be there in the supply system. Any supply system is not so ideal. It has some resistance instead, in place of resistance also will be there, but resistance is less problematic than inductance in this case. Okay, so this inductance presence in this side and an inductance presence in the DC side is like challenging each other. When they are conducting, they are in series. There is no issue. That means the current in the inductor level has developed. But when they are when the commutation is happening when first conduction, after first conduction, you try to turn off these 2 thyristors and bring in TH2 and TH3. So you have no other way of doing it other than just fire these 2 things, because you cannot turn off TH1 and TH4 immediately. It will be turned off by the circuit condition, and the circuit condition is that it has to see negative voltage and its current has to get transferred. But that is not happening in this situation, because this inductor is also would like that this current is continuous. So this thyristor 1 will not immediately turn off. Its current will not immediately die, and it will not pass its current to TH2. Right? That is not that will not do. Whereas here it was doing it. So what is the consequence of that is that you will get 2 isolated circuits. You will get 2 isolated circuits. One circuit is short here because there are 2 inductors and the current is continuous. One circuit is here and they are shorted. This is shorted. This all 4 thyristors are conducting during the commutation phase. all 4 thyristors are conducting, and the load is a continuous current. I am indicating the continuous current by a current source, so that you are unambiguous. Load is continuous current. So load current is ID, and this continuous current is maintaining itself through the shorting. One part is here, another part is here. So this that is a load side is now shorted. That means V rectifier is equal to 0 at that instant, is equal to 0 during commutation. Right? This is the difference. We'll give a more analytical thing for 3-phase thing. You can yourself do it. It is not so difficult. So you can yourself do that. It is a sine wave. It's a sine wave. You are fired at this thing. So here, this is the zone where this bridge is shorted. And the bridge shorted means what is the equation? At this instant it has been fired. So this value is alpha. So you will write is LC. This is LC. LC di by dt during the commutation is equal to Vm sine alpha. That is the voltage here. And assuming that this duration is very small, you assume that this sine alpha is almost constant, because this duration is called mu duration, very small duration, because commutation is happening. Because this value LC is not too large. It is a commutation. LC not large, but it is existing. It is like a non-ideal leakage inductance. This is called leakage inductance or commutating inductance, not large. So therefore the equation, this is a good enough equation. This is a good enough equation. And this equation is saying what? This is saying with respect to this current IAC, L di by dt, LC dic by dt is equal to VMC during commutation, only during this commutation. So now you know how I can write it. DIC, what is DIC? Initially it was a current ID. ID is the load current, it was carrying the load current ID. And after commutation, what it will happen? Minus ID, because that time TH3 and TH2 will conduct. At the beginning of the commutation, TH1 and TH4 are conducting, and it is carrying an ID in this direction. When at the end of the commutation, what will happen? TH3, TH2 will conduct, and therefore the current in the input side IAC will be minus ID. So what is the difference current? DIC is equal to 2ID, and dt is the time what we want to find out, that mu duration. Okay, so delta t is time mu, or in an angle it is this. Let it write it as delta tc, that is the commutation time, is equal to Vm sine alpha. So what is the consequence? You can from this you can find out what is delta tc. So the delta tc is nothing but LC 2ID by Vm sine alpha. So you know the current, the duration during which this commutation will happen. And commutation happening, what consequence does it have? It is a consequence, because during commutation the rectified voltage is this 0. For how much duration? For delta Tc duration, the commutation duration. So what is the average voltage? Average voltage is therefore reducing, other than what it would have been if there were no leakage inductance. If there were no leakage inductance, the output voltage average would have been 2 Vm by pi cos alpha. Now it is reducing by this time into V sine alpha. Then you take the average of it. That is the volt second it is reducing. How much volt second it is losing? It is losing that Vm sine alpha. And for how much duration it is losing? Delta Tc. Right? So the volt second it is losing is Vm sine alpha into delta Tc. That is the volt second it is losing, and the average will be divided by T by 2, because every commutation, one commutation per cycle. So the average thing it is losing is T by 2. Average voltage it is losing is T by 2. T by 2. So this will be the expression of the reduction in the voltage. So this is the voltage that you will get now is 2 Vm by pi cos alpha minus how much? Vm sine alpha into delta Tc by Tc, that is the commutation time, divided by 2 by t. 2 by t is t by 2, sorry, t by 2. So 2 Vm by t into this, right? So this is the factor, right? So Tc has been, this is the now rectified voltage. This is the rectified. This is the reduction that has happened due to commutation. Due to commutation means the inductor, there is an inductor at the AC side, right? So Tc has been found out. Tc is now, what is the simple expression of Tc? Tc is equal to, Tc was LC delta Tc is equal to nothing but LC 2ID by Vm sine alpha. So what is the expression then if I put it? 2 Vm by pi cos alpha and to Vm into Tc is equal to 2 into 2 minus delta Tc to LID by Vm sin alpha. So this is equal to, let me put Tc Vm sin alpha is equal to LC into 2ID, okay, by LC into 2ID by T. So 2 Vm by pi cos alpha, 2 by T, T is equal to omega by omega T is equal to 2 pi. So it is 2 pi by omega. So 2 pi by 2 omega into LC into 2 ID. So 1 2 cancels. So it is equal to 2 Vm by pi cos alpha minus 2 ID omega LC by pi. So this is the voltage drop in happening in the rectified voltage, right? So we'll do this expression on the in the case of a 3-phase rectifier. So in the next class we'll start 3-phase rectifier, but you should remember that the consequence of having a leakage inductance in the continuous conduction mode is that the rectified voltage will be less than what it would have been if there were no leakage inductance. Okay, if there are no leakage inductance, then it would have been 2 Vm by pi cos alpha, but with leakage inductance this drop will come. 2 ID depends upon the load current ID, omega LC as if it is like an impedance, omega LC by pi, right? So in the next class I will start 3-phase converters. Thank you.